I'm Professor Somnath Roy from Department of Mechanical Engineering at IIT Kharagpur. I'm jointly with Center for Computational and Data Sciences. I work in the area of computational fluid dynamics. We are working on moving boundary flows with a focus to bioflyers and arterial flow, some of the applications of including different material processing, etc. We work with an in-house code which uses an immersed boundary method for solving flow over complex and moving geometry, and I'll discuss about OpenACC based acceleration of that code. The outline is that we'll briefly discuss about what is immersed boundary method, what are the important steps in that, and then we'll see what are the compute heavy parts in this code and what are the steps towards acceleration of this code. While getting a OpenACC accelerated version, we need to do some algorithmic modifications and also some steps towards performance optimization we'll discuss. I'll briefly discuss about multi-GPU parallelization and multi-scale framework, and then I'll show you some of the performance matrices. I must acknowledge that the entire development has been carried out by some of my PhD scholars, among them Mr. Apurv Raj, Nandan Sarkar, and Devajyoti Kumar. They took the lead in the code development activity. Some other scholars also participated in this activity, and we have been thoroughly advised and supported by Mr. Bharat Kumar Sharma, GPU advocate from NVIDIA. The method that we'll discuss about is the immersed boundary method, which this was first devised by Professor C.S. Peskin when he was simulating blood flow in a heart. Especially, he was looking into the measurements of heart valve. Heart is a very complex three-dimensional geometry, and among them, heart valves go through fluid structure interaction, several deformations, etc., deformation and movement. But what Peskin did that he used uniform Cartesian mesh framework, inside which he has separately described the heart wall, a separate set of points, and obtained the forces that is given by the heart wall on the blood. So these are not given exactly on the grid points, but the heart wall is somewhere in between the grid points, say at a particular point of time. So you obtain the force that the heart valve will give on the blood following some elasticity model. And then in order to compute their effects on the grid points, he interpolated this force in the nearer grid points using Gaussian-like interpolation function. Instead of directly specifying boundary condition, he used these forcing terms into those points in the Navier-Stokes equation and solve the Navier-Stokes equation in Cartesian domain. And this is one of the ways in which one can use a Cartesian mesh framework and predict flow over moving and complex boundary, because the boundary is not conforming with the grid points, and the biggest advantage is that complex and costly grid generation processes can be avoided. For example, if one is using unstructured mesh, there are algorithmic complexities. Also, there are certain models which are well posed for Cartesian mesh framework, and there are difficulties in posing those models for complex geometry, complex grids, calculating the right Jacobians, etc. So those states are avoided. Instead of directly modeling the heart wall, their effects are calculated on the Cartesian mesh points. A variant of this is known as discrete forcing, where instead of calculating the force from some elasticity relation, one specifies the boundary conditions into the Navier-Stokes equation, which the boundary is not conforming to the grid point, and calculates the resulting force there. And then this force is distributed to the nearby grid points. One of the ways imposing the velocity to a ghost point inside the solid. There is another way where instead of imposing the velocity inside the solid, we can impose the velocity boundary condition into the nearest fluid mesh points. In both the ways, instead of working on the forces, because if we think of this equation in a semi-explicit manner, this will be a linear equation. So instead of applying the forces, a more straightforward way can be doing the velocity interpolations directly and applying the velocities on the right points. So the basic idea is that I have a uniform structured Cartesian mesh. Say it might be a non-uniform mesh also. Inside that, using a separate description, I define the solid surface inside which it is solid. And this solid surface is not conforming with the grid point. So identify what are the nearest points of the fluid close to the solid surface. For these points, I cannot define the full stencil and cannot solve the whole Navier-Stokes equation. So what we'll do for the points which are in the fluid and for which the entire stencil can be defined, we calculate velocity using Navier-Stokes equation for the points which are close to the boundary, but also in the fluid, but they have a neighbor inside the solid for which we cannot define the full stencil. We'll interpolate the velocity using the boundary condition and the surface and far field data. And for the points which are inside solid, we'll specify the predefined boundary condition or solve the structural equation and put the boundary condition, etc. As time progresses, in case of moving or deformable object, the solid surface will move into a different location. We will again identify the points in this manner and apply and solve it through the same technique. One of the methods for applying the velocity boundary condition for imposing the velocity boundary condition is you need basically some interpolation method. One of the method is second order velocity reconstruction method by inverse distance by Franke. Similarly, there are many other interpolation functions. We'll use a different interpolation function, but this is a very general interpolation function which I'm showing here in case of the points are heavily scattered on the surface. In our IBM implementation, what we have done here that we first define the solid surface as an unstructured triangular mesh in a volume mesh which defines the fluid volume. Inside that, using a normal based search method, we identified which of the fluid points lies outside the solid, which of the fluid points lie inside the solid. And from there, we identify the points which has both solid and fluid vertices, and we identify those cells and term this as the intercepted cells. In the intercepted cells, we have to apply the boundary conditions. Here we have identified intercepted cells which are shown as the blue cells. And now we solve governing equations in the fluid cells. Flow variables at the intercepted cells are identified. The vertices of intercepted cells are obtained through a reconstruction method, which is known as forcing or simply a second order. We are using here a quadratic interpolation method, which uses the boundary condition at the surface along with the far field fluid velocities. And cells inside the solid are directly set into motion. And there are some of the application in aerodynamics, application in heat transfer, application in arterial flows, or applications in continuous casting or different other material processing. We try to predict what is happening, how the physics and different engineering parameters can be predicted. The issue comes when we try to think about large-scale industrial problems. Solution of incompressible Navier-Stokes equation, which we are solving here, we are using a marker and cell method that requires solution of pressure correction equation, which is basically a matrix equation. And if we have n grid points, then the complexity of this problem is of the order of n cube number of operational steps have to be done. So when we talk about large three-dimensional geometry, we have few million meshes, the number of operations are very large. Along with that, we have to search for the intercepted cells. Say we have around 10 to the power 5 mesh points and 10 to the power 6 volume cells. So there is a very expensive search because each surface mesh point has to find out what is the nearest cell, whether that cell is intercepted or not, and what are the weights for the interpolation also. So if we do a gprop based profiling, we have an in-house Fortran 90 solver. When we have done the gprop profiling, we saw that Poisson equation is taking 74% of time, surface tracking is taking 13% of time. For a fixed body, this is one-time affair, but when the surface is moving, then we have to do it in each time iteration. And momentum equation is taking around 6%. So in order to go from less than a million or a million cell to tens or hundreds of millions of cells, we have to do a parallelization. So we follow the triad. We are trying to analyze the code, parallelize the code, and then we'll see how we can optimize the performance. In analysis, it is found out Poisson equation can be solved using different solvers, but among them, the most explicitly a solver that can be placed is a Jacobi solver. This can be very well parallelized. If we think of something like general successive over-relaxation solver or a matrix vector product based solver like Rylov subspace solvers, compared to that, Jacobi solver can be very easily parallelized. We can work with smaller amount of memory. We can consider the diagonal nature of the matrix, and it's completely explicit. However, it has a very slow convergence rate. So if we think of building our code over a Jacobi solver, we have to do certain modification. when we are trying to apply surface boundary condition, this part is difficult to parallelize because we have a loop we have some points which are inside fluid for which Navier-Stokes will be solved, some points which are where we have to implement surface boundary conditions for which interpolation has to be done, and some points are inside solid for which some other equation has to be fitted. So we'll encounter a lot of if-else statement, and that can lead to warp divergence. And also the reconstructing parameters, that what are the weight functions for the interpolation, that if we need to store that, gives memory overheads in terms of storing the fluid points data, and updating the data, copying it back to GPU from CPU, etc., takes substantial amount of time. We are here for mass conservation and reducing pressure fluctuation. We are solving in the original code, we are solving an extra constant equation in the intercepted cells, which is expensive for large scale problems, and we may drop it and think of some other algorithm. So what we have done, that instead of directly going to parallelize, we tried to reinvent some of the points here and do some algorithmic modifications. Instead of Jacobi, we thought of a red-black successive over-relaxation solver, which gives a faster convergence, which uses some of the properties of an implicit solver, and we have made certain looping for removing warp divergence there. For the different solution strategy at different cells, we have grouped the cells as fluid, intercepted, and solid cells, and made a three different 1D data structures and ran the loop over that. Used a compressed diagonal storage for matrix because it's a regular Cartesian mesh along x direction. All the points will have same weight in I+1 and I-1 in the matrix location. Similarly, in 1nz direction. So using that fact, from 7nx nynz requirement of memory for the diagonal storage, we reduce the memory to 2nx ny plus nz. And this helped in handling 100 millions of cells in single GPU, which was earlier not possible. We removed SOLA, which was an optimization on the intercepted cell for controlling spurious pressure oscillations, used a different method called field extension. We have simplified the reconstruction scheme, interpolation scheme using one weight point, and dynamically the arrays are allocated, especially for a moving boundary method where we need to store certain fluid data. Then we are dynamically allocating memory at every time step using create and discard. Then we use that red-black SOR method. So the basic idea is that some points are grouped as red and some points are black, and we learn two different loops for the iteration for matrix solver. If we use an if-else method for red-black that encounters warp divergence, so we group red points and black points separately, and we got additional 10-15% time saving. And for smaller problem, also red-black solver gives 30x plus performance. Now we put everything to try to put almost all parts of the code into the GPU, and we observed that GPU time is substantially reduced than the CPU time. There is a small overhead in memcopy because we are anyway working with a much compressed matrix format, as well as the updates are on terms of the vectors only. Once everything stays in the matrix in the GPU, we are not copying it usually much back into the CPU unless extremely needed. And we can see that it is giving 100 to 139x performance in V100 GPU compared to V100 and A100 GPU. We can see in A100 GPU memory copying time is substantially small. Along with the Poisson equation solution, the iterations, they're much faster in A100 GPU. And one can see that we get a good benefit in terms of performance at 12 million cells in A100 GPU. The computing time is nearly half, close to half, and we have solved the robotic butterfly simulation in A100. Now we tried to further optimize it, used a different surface tracking algorithm which gives 3 times speed up. Instead of allocating and destroying the memories, we are using declare directive with create clause, and which especially for the moving boundary problem, so trying to use a fixed width allocation for the memory, fixed allocation for the sum of the memory variables with certain padding, which is giving better performance. The convergence is not checked every time, but after 50 iterations, that reduce the overall memory copying steps and reduction operations when we are checking convergence among all the cores, etc. and used a Z directional domain decomposition, overall performance improved by 1.5x factor. So you're getting around 200x performance for something like 40 million cells. And we solved flow through mechanical heart valves in human aortic geometry and did a direct numerical simulation. Resolved it up to 3 Kolmogorov length scale. Then we went to do multi-GPU optimization, where basically the domain is decomposed into multiple subdomains and there is data exchange between the domains using MPI calls. We've seen that asynchronous MPI gives 1.2 times speed up compared to synchronous MPI, and ring topology based GPU arrangement in DGX system gives better performance. So some of these aspects on how the domains will be pinned to different GPUs and what should be the different MPI calls for data exchange, that has been investigated on. And now one can see that it scales up to 16 or 32 processors, and we get the data for different platform. Like in V100 DGX, we can see that it is almost, the search is almost fully parallelizable without any drop in performance. But the Poisson equation gives around 2.8, 2.9 times of performance when we have a larger mesh in 4 GPUs. And in 32 GPUs, we can also see that we are getting good speed up. Compared to 16 GPU, we are getting almost twice speed up in 32 GPU when you are solving the Poisson equation. And we got around 6.7 times speed up in 8 GPUs in A100 DGX using NV switch, which is a much faster data transfer rate, and we solved the arterial flow problems. Now we are looking into multi-block problems, so multi-scale problems, where some of the fine scale phenomena at one particular zone can be put into separately, and using same domain decomposition method and assigning different block to different GPUs. And here we can also see that along with the Poisson equation, AMGX library, if we can use a beta solver from the AMGX library, we can get better speed up. So these are the basic development activities here. In conclusion, we have discussed immersed boundary solver for moving and complex boundary, the steps for OpenACC based parallelization. We're working on multi-GPU implementation, multi-scale framework is also presented. We're getting more than 100x speed up to 80 or 100 million cell problems. Some cases for larger problems, it is around 200x speed up.